Okay, so we're talking about surface area. So your the next homework online is due Wednesday morning at 8 a.m., 9 a.m. Wednesday at 9. So hopefully you've started that. If you have not started it, don't wait till tomorrow night. Okay, start tonight or this afternoon. Okay, we're talking about surface area, and we said that if we used like ribbons, remember this? Ribbons based on dx, it didn't work. So that would mean sweeping out a circumference, right? Sweeping out a circumference parallel to the x-axis in every interval. That didn't work. Can you be on phone duty, please? Phone police coming around. So instead we said, yeah, it's the circumference of our ribbon is sweeping out the surface area, but we don't want it parallel to the x-axis, but rather like this. At the beginning of every interval, we want that so that's a large delta x. Here's a smaller delta x. So what's different about this? So this is according to ds, right? ds is tangent to the surface at the beginning of every interval. Tangent along the tangent line to the surface at every interval. And so when our circumference of our ribbon follows along ds, which is on the diagonal, like tangent to the curve, then when delta x gets small, it will find the surface area for us. Okay, so does that ring a bell? And so if we were taking those ribbons that were parallel, then it didn't give us the right surface area, even when delta x got small. So review the video to remember about that. So let's start applying this stuff. So here is the function g of y equals ln of y. And that's a little different than what you're used to. Why? Because now I'm saying that y is the independent variable, right? Y is the independent variable, not x. And I want to graph it as such. So I want to graph the independent variable on the y-axis, not the x-axis. And that would make what? That would make my values of the dependent variable be what coordinate? You said x. Agree with that? Right. So it's like we're going to flip it around, right? So all our life we're used to independent variable being on the x and dependent being on the y, but that's just convention. There's nothing intrinsic about the coordinate system that independent has to be on x and dependent has to be on y. So if we really understand it, we should be able to flip it around and make sense of it, and there should be no problem. So let's practice that because we don't do this often. So how am I going to tell GC to graph this? How am I going to tell GC to graph g of y equals ln of y, making y be on the independent variable on the vertical axis? Yeah. Y equals g of y. Is that what we want? So using y and x and GC is specifically using x and GC is specifically x-axis, and using y and GC is specifically the y-axis. Yeah, so what do we want where do we want g of y to be? That's the dependent variable, right? That's the output, and we want that to be on which axis? X. So we want what? X to be g of y. So that's going to take all the output of this function, the dependent variable, and put it along the x-axis, and make the independent variable on the y-axis, and then I want it from 1 to 4. So what do I do here? So I only want it from y values from 1 to 4. So I should write 1 less than or equal to y less than or equal to 4. Okay, and there it is. Let's say, so just so we make sure we're understanding this graph, let's pick a point and let's interpret it. So I'm going to pick a point in this graph, just anywhere here, just right there, say. And this is the point 1.056. Is that what that says? My eyes are going bad, and that's small. 1.0. Comma 2.875. So we want to interpret those coordinates according to g of y equals ln of y. We're interpreting the meaning of that point right there that I have the crosshairs on. Okay, think about it. Tell the person next to you, what's the meaning of these coordinates relative to the function g? What do they mean? Think about it, and then tell the person next to you. Okay, what do we think? How would you interpret those coordinates in light of this function g? I'm gonna, yes, sir.
At value of y equals 2.87,
Uh-huh.
x value would be 1.056.
Okay, that's true. So, but tell me in terms of g, right? That's right, absolutely right what you said, but I want to relate it to g. So the function g of y, yes, sir.
Y is the independent variable?
Right? Yep. So, therefore, yes, ma'am.
G of 2.875 equals 1.056.
Right. So yes. So everything you guys said was correct. So we put it all together, and so when y is 2.875, then this value is what? What value is this? How does this? Where did this number come from? What is this value? Okay, it's g of y, which is ln of 2.875, right? So this is the, we got the dependent variable here. This is the natural log of 2.875. Or like you kept saying, g of y, awesome, g of y, that's right, g of 2.875. So here's our independent variable. We start here, and then the corresponding value of x is the corresponding value of natural log of that value. Let's say x. We start here with y, right? Start with a y value. The corresponding value of x is the natural log of that y value. Okay, so we're turning the tables. Doesn't make sense. Okay, so let's just make sure we understand the function. So now let's do, I want you to determine the arc length function for g in terms of y. So I want an arc length function that tells me how much arc length has been accumulated, the accumulation of arc length for any given y value. See if you can write that. So can you define that arc length function? Go. Mason here? No Mason? How about Eric Plitz? Where's Eric? Show me. How'd you do on this? Tell me. Did you get the arc length function for g in terms of y? Okay, so so what did you write? Wait, so the integral, did you say the integral from 0 to y? Okay. Okay, okay, t, good. And then? Okay. She wants squared. You want squared? Yeah? And plus? And we called that lowercase s. S of what? S of, so yeah, we're going to use our new notation, the two argument function notation, meaning a and y, and so then this would change to? But we want a function. 1 and 4 gives us just one arc length, right? We want a function. We want every arc length for every y value. If you do 1 to 4, you just get the whole length of the red arc, one value.
1 and 1.
Okay? So right, so if we can choose to make that a value then any value of y starting from 1, right? We can make it 1, we can make it 2, we can make it 1.8, anything we want. All right? Okay, let's see if we came to the consensus there. This is what I have. Is that what we said? Yep. That's what we said. Good. All right, and so next. So now I want to do something that's, again, a little bit unfamiliar, but great practice for our understanding of functions and graphing. I want to graph the arc length function over here in the right-hand pane. So that the independent variable of that function is on the horizontal axis. And what was the independent variable of the function? Y, okay? So I want y values from our original g function over here to be plotted on the independent axis, on the horizontal axis over here. And then on the vertical axis, I want the arc length of this function. Or in other words, this. We're graphing this function, our arc length function, and we want to put the independent variable, or y, horizontally this way, and then have arc length vertically. Okay, so that's back to what we're used to, right? Back to what we're used to for functions, but we're grabbing from a situation that's opposite of what we're used to, right? Where the independent variable is on the vertical axis. Okay, but I want to do that over here. So how would I do that? What should I type in GC so that it's going to plot for the y value along here, it's going to give me arc length. It's going to give me a graph of arc length versus y values on this graph. So what do you think? What should I type in? So let's make sure we see our graph. All right, so there's our function, and I want to know, what do I type in to graph this? So remember, x and y in GC, x is telling GC horizontal axis, right? Y is telling GC vertical axis. So what is it that I want on my vertical axis? What is it that I want on the vertical axis? That I'm going to tell GC y for that. And what is it that I want on the vertical axis?
S of g of y or a comma y equals x.
So what do I want on the y-axis over here, on the vertical axis? This is my arc length, right? So how am I going to represent arc length here? And I want that to be on the vertical axis. Yeah? Oh, sir. What's that? Someone started to talk. Y equals, right? So y equals telling GC. Put on the y-axis, what? What do I want on the y-axis? S of g, this thing, right? Now. But what do I want? What do I want on the x-axis over here? All right, so my independent variable over here is what? So this is saying my y value's here, but I want them here. So how do I need to change this? Yep. So what does this do? It says put on the x-axis whatever was in the definition of the function here, right? Put on the x-axis whatever we defined in our function as that second argument, y. Okay, and then a little this is a convention in GC. In order to get it on that second window pane, I need apostrophes on my y's and x's. yeah, quote, a single quote. So now notice, this is not derivative. This is just GC's convention for graph on the right-hand window pane. So I got to put that y, this is not y prime. This is not the derivative of y. This is just a plain old y, but right-hand window pane. So I got to do that for the y's and the x's. Okay, so what do you think that will look like when I turn that on? So what is this going to do? It's going to be for y values over on this graph, it's going to put those y values here, and then give me corresponding values of arc length here. So can you predict what that will look like? Yeah.
That's a quick question.
Yeah.
Would GC not be confused that the y is the top of the integral compared to when we switch to x?
So this definition, this is not, in the definition, it's not thinking about y and x at all here. It's not, when you define a function, y's and x's don't relate to the graph at all. So it's just saying that it's just going to be our arc length, and this is our independent variable. We know that's from the y of our graph. Okay?
So we would have to change the integral from a to x. We could leave it a to y.
Yep. So as long as these two symbols match, it doesn't matter what they are, because it really comes down to this, g of t. Right? That's really the key, that this is the dependent variable of the function. Did that help? Yeah, okay. All right, so what is this graph? When I turn this graph on, what is it going to look like graphing arc length of this red graph as a function of the y variable over here? What's it going to look like? Can you sketch it? Yeah, so what do you think? And where's the starting point there? When you started your finger, you started here. Where is that starting point going to be? On this graph. Where? What's that? On the x-axis where? At 1, right? Because when y equals 1, how much arc length do we have we accumulated? 0. We're going to accumulate arc length starting from 1 going up like this. So at this value 1 is when we're going to have 0. So we're going to start at that point and do what? As we increase in our y value up here, what's going to happen to the arc length? Increase, right? So it's going to be something like this. Let's turn it on. And we want this from what to what? Again, 1. But what's from 1 to 4 now? Right, on the graph, x. Okay, so I'm going to pick a point. Again, let's pick a point. And then we're going to practice interpreting the point so we really know what this graph is showing us, okay? So this is the point, 2.640, is that right? 2.64 and 1.92. I can just barely read that. 2.64, it's easy on the screen. 1.92. Okay, so think about what are the meanings of those. What's the meaning of that coordinate pair, that ordered pair? In light of the situation, in light of the function g, in light of what's going on over here. Think about it, and then tell the person next to you. Everyone's listening or talking to someone. Where's Alyssa? Alyssa Sola, right here. Hey. What did you say? So the ordered pair 2.64, 1.92 means what? Okay, so you said at 2.64 the arc length is 1.92. So when you say at 2.64, exactly what does that mean? At, so 2.64 is what exactly? The graph on the left. So 2.64 here on the vertical. Okay, so at 2.64 on the vertical, is that about here? What is the 1.92 again? How much arc length since? Since 1. We can't draw on a chord. It doesn't work. All right, there we go. So what should I draw to represent 1.92? What could I add to this drawing to represent 1.92? The meaning of the 1.92. How can I illustrate that on this drawing? Yeah.
Just go ahead and just draw the line, go straight down, stop showing the curve, ultimately.
Straight down like this? Is that what the 1.92 is? Like this coordinate, like kind of 1.92?
I was just talking about the length of the actual graph of that speck, so
Okay, so you didn't mean straight down. You mean along the here?
try and get like the hypotenuse rather than the angle being.
So the length of this right here is 1.92. The length of the arc is 1.92 when we've gotten to y equals 2.64. That's what you should have talked about. That's the meaning of that point. When we got to 2.64 in y, the amount of accumulated arc length so far was a length of 1.92. Doesn't make sense. Is that what you said? Is that what you imagined? Okay. Attendance quiz. Attendance quiz. Oh, I had it here somewhere. It's 271. Where was it? Crying out loud. Had it ready. Monday 23rd. It is published. Water. Water. Is your ticket into your attendance today? Water. Does it work? Are you in? That's such a weird word.
Water?
Yeah, I'm looking at it now. It's like, that's so weird. One answer this time. This is not multiple answer. There's one correct answer. I'll show you the graph again. So the S, it's S sub G, right? So I couldn't do a subscript in your answer choices. So all the S choices are S sub G.
Yeah.
30 seconds? Can we get it locked in 30 seconds? I'm making these as easy as I can. So don't doubt yourself.
Okay.
Everyone done? About to lock. Okay, locking it. All right, so now, how can so what was the answer? S sub G of 1, 4. How can I see that in this graph over here? That same value of the whole arc length. What should I do? Or where do I look on this? Is it the whole length of this pink arc? No. Where is that represented? The length of that whole arc, where is that represented in this graph over here on the right? Yes, sir?
The value where x equals 4, the y value.
Good. So if I brought the crosshairs all the way to the end, where x equals 4, the y value on this graph is the amount of accumulated arc length on this graph. So the whole length of the arc is? The whole length of that red arc is 3.3428, the y coordinate when x is 4 on the right graph. Okay, so now let's talk about surface area. This is a little bit trickier, but we're kind of getting this feel for, all right, let's change things up and let's really understand how graphs work by getting out of our, familiar mindset. All right, so surface area. Now I want to rotate that curve about the x-axis, and I want to define the rate of change of surface area with y as the independent variable. So still going up in y. So first of all, let's get a visual or an image of that. What happens when we rotate that around the x-axis? Can you sketch it? Can you sketch the surface of that whole thing from y equals 1 to 4 if that is rotated about the x-axis? Yes, sir?
So we're rotating the left graph around here?
Yeah, we're not, so this is, right graph is going to no longer be about, it's going to be about surface area from here on out. So just back to the original graph. Original graph of g of y equals ln of y. I want to rotate it around the x-axis. And what am I going to get when I do that?
So just the shell?
Surface area is just about the shell, right? So we're not filling it up. We're not doing volume like we did before. We're just going to rotate this and make a shell, and then we're going to track accumulation of surface area of that shell. So what will that look like?
I can't draw.
What's that?
I can't draw.
You can't draw, okay? Can you explain what it should look like?
It should look kind of like a bell.
A bell, yeah, like a megaphone or like the bell of a horn, right? Something like this.
Like a vulture.
Yep. Right, sideways. Something like that. Now we're not going to fill it up with cylinders like we used to for volume, but we're going to track what? So as y increases, we want to track how much surface area has accumulated. Okay, so now our these ribbons that are angled, right? The ribbons that are not parallel to the x-axis but angled. So those, even though we're doing it in terms of y, because we're rotating around the x-axis, those have to be like vertical ribbons. Okay, so one such ribbon would be, so remember, doing ribbons like this will not work even when the independent variable gets small. That will not work. What do we need instead? According to ds, which is in the current interval, starts with the tangent to the curve. Let's do another color here. Orange. No, too much like red. How about green? So we're going to start with ds. And so that this is like part of a cone, right? So those edges have to be, oh, that's not good at all. Where are we at? Those edges have to be parallel or tangent to the curve at the start of the interval. And so that's going to be our typical, what we call a frustrum. I call them ribbons, so frustrum. It's like a slice of a cone, right? It's because it's angled at the edge. Okay? So even though y is our independent variable, we're rotating around the x-axis. So those frustrums, those ribbons, have to be vertical. They have to be this way because of the rotation. But we can still do this in terms of y. So anyone think they can define the rate of change of surface area for this? Anyone think they got it? Volunteer. Yeah.
Isn't it 2 pi g of t times the square root of 1 plus
2 pi. So the radius is, okay, you're saying the radius is what? The radius is x, y, change in x or change in y? Y coordinate. Okay? So the radius is a y coordinate, so it should be 2 pi. So first of all, what is, we're going to start off with our left-hand side for defining the rate of change function, or rate of change, right? So this is, yeah, so what do we want to call that? Rate of change of surface area, and I'm going to put another little subscript g.
What does the G stand
What does the g stand for? Function from function g, right? Rate of change of surface area from function g. Okay? In terms of y. Okay, and you said 2 pi. So, what's the radius? The radius is y. And then, do we want to change that to g of y? Let's put that on hold. And then we got square root of? One plus? What?
dy over dx squared?
Okay, so derivative of g with respect to y squared. Now, let's go back to this. Do we leave this as y or do we change it into something else? So the radius is the y coordinate. And what is our independent variable? So that's in terms of y. Do we need to change it?
No.
Don't change it, right? It's already in terms of y. It is y. Our independent variable is y. The only time we would change this is if, say, we started with something that had x's in it, and we needed to get that expression in terms of y because y is the independent variable. But it is in terms of y, so we just leave it. So you see that the y coordinate is our radius, and so we can just leave it because that is our independent variable. Does it make sense? So let's see if that agrees with what we have here. Is that what we said?
Yes.
Okay, so now I think we're ready to write the surface area function with y as the independent variable. And take advantage of what we just did. This time we separately wrote out the rate function. Take advantage of that. Make your definition as simple as you can. All right, yeah. So to review, so this is a good way to think of it. What sweeps out surface area? The circumference sweeps out surface area, right? The circumference of this ribbon. Okay, but not according to x horizontally in each interval, but according to arc length. That's why we need the square root part. So we're sweeping out circumference, but according to arc length, which is tangent to the curve, right? So that's why we get these little slanted edges on our ribbons, not horizontal. Doesn't work. That was from last time. So sweeping out the circumference according to arc length. And that gives us surface area in the end. Okay, let's see here. Spin the wheel. Where's Matthew T? Matthew T. How'd it go? What did you feel?
Still working on it.
Okay, did you get started?
I just have the
Big S, good.
8
A to y, excellent. So what's the structure of this going to be? Good, integral. From A to y, excellent. So here, okay, so we could write, you want to kind of rewrite this? Is that what you're starting to do?
Yeah.
So there's an easier way to do this. Now that we've defined this, what could we do? Yeah.
Square root, so you could take the square root of 1 plus r sub s of g of
Yeah, so what we need is the rate of change function, which is this. We could write all this out and put it in here with t's, or we could just, r sub s of g of t So we're going to use what we already defined. We already defined that function, the rate function, so we don't need to type it out again. We'll use function notation to do it, right? But now we need the t in there. So if you rewrote this with t's and put it here, 95. If you put this in, a plus, 100. Is that what we said? All right. So now I want you to represent the total area of the bell, right? The total area of the bell of the horn. Can you represent it? And then we'll plug it into GC and let it tell us what that area is. Go. How do you represent the total area of the whole surface?
So I plugged in 1 for A.
Yep.
And 4 for Y.
Yep. And so then what was your whole answer?
Like the actual that worked out answer.
No, like the answer to this question, what would you write down to represent?
So I would put S of G of 1, 4. 1 or 0? Oh, sorry.
S sub G of, and then anything else after that? Like equals something or? Nope. It's just that. And as soon as you get that in, GC tells you what the answer is, right? So that's all you need. S of G of 1 comma 4. So at the total surface area of the volcano, the sideways volcano on the lateral surface is 51.184. Now that does not include the opening here, circular opening, or the circular opening on this side. We're just tracking along the red curve, so it's just that lateral surface area. Questions on that? All right, now we're going to do the same thing we did before. Over on the right-hand pane, I want a graph make this bigger. I want a graph over on the right-hand pane. I want y on my horizontal axis, the y values from the left graph on the horizontal axis over here, and then the resulting on the vertical axis is surface area. Okay, so can you write down what I should write in GC to graph that, and then predict what the graph will look like? So I'm going to graph the surface area function on the right-hand pane, independent variable on the horizontal axis, surface area on the vertical axis. Where's Philip? Perez? Philip? Brett? I thought someone raised their hand. Where's Philip? Oh, okay. Did you get this? How will I graph over here? Independent variable, horizontal axis, surface area on the vertical axis. Give it a shot. So just think about, so when we say y, that's going to tell GC this vertical axis. So what do we want to be on the y? So we say y equals, and then we're going to tell GC what we want on the y-axis. What is it that we want on the vertical axis? What quantity? Do we want arc length? Do we want surface area, right? And so what is my surface area?
S of G.
Capital S of G. Okay, and let's just put in what we know A should be. What should A be? 1, I'm going to start from 1. Comma. So this is telling GC now what I want. I want to tell GC that my independent variable should be on the x-axis. So I should put x, but I need the little apostrophes to make sure it opens on the right-hand graph. All right, and what did we get for arc length? For arc length, we got something like this. remember. It was bend. Did it bend down or bend up?
It was down.
Bending down a little bit.
Awesome, sir.
Okay. What do you think the surface area graph is going to look like compared to what the arc length graph looked like? Okay. Yeah.
I think it's going to slope upwards
Slope upwards.
because as our y increases, the radius gets larger.
What was the total length of the curve? What point? 3 point something? And what's the total surface area? 51. Where's this graph going to start? Is it going to start at the same place that the arc length did? Yeah, but by the time we get to 4, it's going to be at... Right, because surface area is tracking all of this area, not just a length, right? So how will it compare to this? It's going to go like this? It's just going to creep up like this? No? It's going to shoot up much faster, right? Okay? So I'm going to do 1, 2, 4. Right? So as soon as y starts to change, surface area accumulates much faster than arc length. Why? Because it's like all the area all the way around this volcano. So I need to zoom out here on the y-axis. So now my sketch for the arc length is not accurate at all because it would be down like really shallow down here like this. Okay, let's interpret a point. Practice here. Oh, I don't know. Here's 2.234 and 14.821. Actually, 8.2 if I round with a 5. Okay, so think about what's the meaning of those numbers relative to my volcano. What are the meanings? What's the meaning of that ordered pair relative to the volcano? Explain it in terms of the volcano. Think about it. Tell the person next to you. There we go. Okay, Landon. Landon Meyer. Where's Landon? Okay, by the end of the semester, I'm going to learn names, so you can't hide. How about Sahari, Ravi? Drop the class. Okay, he's off the hook. How about Connor Murphy? Connor. Oh, I have something. All right, so just somebody, a volunteer, somebody new. Somebody new. Yeah, please.
So at 2.234 on the original paper, so the y value would accumulate 14.22 units.
Awesome. She said at 2.234 on the y value over here on this graph, which is somewhere around here. So by the time y is 2.234, all this surface area, only up to y equals 2.234, is the 14.82. But not past any higher y value than that. Is that what you said? Okay, so now I want to rewrite, so same rotation, but I want to rewrite the surface area function as a function of x. As a function of x being the independent variable. So I want x to be the independent variable. I want the same rotation, the same frustums, but I want to write that surface area in terms of x. See if you can do it. Okay, so we're going to start with the inverse function. The inverse function is how would we write this exact same curve, y is a function of x? So x is g of y was ln of y is f of x is, the inverse of natural log is e to the x. So I defined f, it's the same red curve here, but y is a function of x. So my rate of change will be, the radius is still the y coordinate, but now in terms of x, that's when you have to change it and do e to the x or f of x. Does that make sense? It's still the y coordinate. It's the same frustums. It's the same ribbons. They still have that vertical coordinate for y. Yeah?
You didn't take the derivative of x under the.
I did. What is the derivative of f of x? Remember? Yeah. No, good point. It looks like f, right? But what is the derivative of e to the x? E to the x. So, yeah, that's good observation. Just remember your derivative is e to the x. All right, so now there's my rate function, or my accumulation function. Now it's going to be from a to x. For my, this is my rate SF. So now I want to graph that. What will I see? Where will this one start over here? Where does, in terms of x, where does surface area start accumulating? 0. So this one's going to start at 0. And then it's going to be a different curve, but when it gets to x equals this value, what should the y value be over here? 51, the same as this. So let's turn it on. So this is according to x now. X starts at 0, different function, but by the time it gets to the final x value, the total surface area is the same. It's the 51 point something. So this is that surface area function in terms of y from 1 to 4, and then x from 0 to, what is that? ln of 4. Same final surface area shown by the y value of this graph.